and I'll be talking about applications of physics for neural networks. We'll do some like a really, brief application on a dampened oscillator, and I'll be talking about how these work and why these work, etc. So, purpose and what to expect. It'll be a really introductory exposure to PINNs. It's intended for undergraduates with not much knowledge on neural networks. We'll keep it simple, introductory, skipping too much detail and intricacies, because these are actually like proper fields that people can actually get PhDs in. So there are a lot of like intricacies we can be talking about, but yeah, we'll be skipping those because we're time constrained. As well as that, we'll skip some math theory, and some details on how to use PyTorch. And as a side note, PyTorch is pretty cool. You guys should look into it. Normally, these topics would have like entire grad school courses. So yeah, we'll be like, if you look up, you'll find a lot more information. So yeah, and I'll give you some further readings at the end. Okay, so insanely short introduction to neural networks. So as everyone might have heard of, for example, ChatGPT, or I don't know, DeepSeek, all of these are really complicated neural network models, and they're essentially trying to mimic the brain, but on a really, really smaller scale. So these things, can the camera see me?
Yes, I'll try.
Okay. So these things, these points are called the nodes, and these are called the connections, right? So in a neural network, what we are trying to do is we're trying to find some relation in a data, right? So just like how a brain learns stuff over time, we're going to make this neural network learn stuff over time. So we'll give it a input layer and an output layer, and between these we'll have a bunch of hidden layers. But for this case, we only have a single hidden layer, right? So we give some input values into the input layer, and then these weights. Okay, so for each of those input layers, let's say we input A, right? And then we want to achieve the next value in this layer. So what we do is, we first, each of these connections would have some kind of a, how should I say this? A weight. So we're going to multiply A times W, and then sum up all of these A times W's, because there will be more inputs, right? Let's call this B. This would be B times W2. We're only talking about the single neuron. So this single node. We're going to sum all of these up and then add a bias on top of that, which would be plus, I don't know, something C1, right? So we can essentially represent everything in matrices this way. But to be exact, this thing is only for this specific neural network. If you have more layers, you would have more terms over here, right? So when we calculate these values, these biases times the input layer data and plus a C1, what we are doing is we want to normalize this data as much as possible, because think about it this way. Our input values can range in a lot of like values, right? Like we can have an input data between, I don't know, 0 and 1 trillion. So there is a chance that when we do this, our result in this single neuron might be, I don't know, like 10 to the 20. We don't want that, because computers are limited by their internal structure, and I don't want to go into too much detail, but we want to keep everything as normalized as possible so that we can maintain as much as detail as possible, because some computers with some number systems might want to limit, which is truncate some numbers, right? So what we do is we input this into a function, so that we can normalize all our results. There are a couple of functions that do this, but a really popular one is the 10H function, which is as follows, right? So you would have the value of the 10H function as this. So This would be -1, this would be 1, and there you go. With all of the input values, you can get a good output value that is normalized. So that's what we do. That sigma here is that normalizing function. So we run this over and over and over. This is going to give us some predictions, right? And we want predictions to be in some kind of a way. But now we have a problem. How do we even choose these W1s, B1s, the B2, and W2s? So there's a way to do this, a really simple way. We can just brute force everything, right? We can brute force for every single B and V values. But that's not a good idea, right? So there's this thing called backpropagation. So what we want to do is, based on our output values, we want to change the weights and biases of these this entire neural network, so that we can essentially do a gradient descent algorithm, right? Instead of doing just brute force, we're trying to do gradient descent on every single one of these weights and biases. So depending on these functions, we're going to update all of the values. The actual functions and formula might not be clear and may not be seen. I thought it would be way bigger in the projector, but anyways. So that's, for now, unnecessary detail, because we actually have some modules in PyTorch that can do these for us. We don't have to hard code these every single time. So yeah, an important thing is also, within each of these functions, we have these things called the learning rate, which is the eta over here. So if you have a big learning rate, think about it this way. You're trying to do a gradient descent, right? But then your gradient descent algorithm, since it has a giant learning rate, because this term is going to be so large, it's going to jump between values like, throughout the entire space. So it's going to just jump over the values and it's never going to converge. But if you have a really, really, really small learning rate, then it's going to take an enormous amount of time to converge into a single result. So yeah, that's a consideration that people usually have to keep in mind, but we're, for now, going to skip that as well, because yeah, this is introductory. So let's apply this to a classical and then to a problem, right? Because we're physicists. What do we even want to do with these neural networks? We want to get some actual results, right? So think about a underdamped oscillator, right? It's underdamped, it's not critically damped, it's going to get dampened over time. And we want to predict this as good as possible, right? So what can we do? We can use the neural networks that we have just described. So we have the problem defined as this. And we have all these details. We know this particular solution for now. We're going to use that. And we have all these different conditions as well. So we want to define a loss function. A loss function is going to help us in this process. So we want to know how far off our predictions are. So there is an easy way to define our loss function. We can just define it as this, right? So we get all of the output values, right? We feed it some initial data. We feed it some like discrete points over here. And then we get some predictions on those discrete points. And then we take the difference squared of all of these points, and then we take the mean of those different squares. So ideally, we would want our neural network to give us solutions where these are really close, right? These results that we're going to get are really close. And if that happens, this loss function is essentially will go to 0. And that's what we want. We want to minimize our loss function as much as possible with different weights and biases, which are these connections here, right? So we essentially write up a code for it. Yeah, we give it some initial definitions, and then we want to get some actual data to work with, right? Because, as I said, we want to compare the results of our neural network and the actual data, right? So using this function, we get some data to work with, right? And then we run the entire thing on the neural network. The actual code is actually in a Jupyter file, and it has way too much detail. So yeah, here what we are doing is we're defining the neural network over here with 32 neurons and 3 hidden layers. What it means is we have this input layer, right? We're going to feed it our initial data, initial x values, which are going to be here. You're feeding it our x values. Then we have these 3 hidden layers, right? Within these hidden layers, all the neurons are connected to each other. So for example, for this one, this neuron in the hidden layer 3, all of the neurons over here are going to contribute for this neuron, right? And then we're going to normalize it using a 10H function, and then we're going to get a result. So we have 32 neurons over here for every single one of them, and we have 3 layers, and we have an output layer, right? Okay, good. So the thing is, as I've said before, we have to backpropagate. We cannot just brute force everything, right? That's not optimal. That's suboptimal. We want to do backpropagation. So what we're doing is we give it some initial data. We forward propagate all of this data. We get some results over here. Then we calculate our loss function, and then we backpropagate, updating all of these weights and biases over here. These weights, right? We want to update them so that we are trying to perfect our neural network to give us a good approximation for our entire data set. So we do this 15,000 times. And a good thing about computers is that they're pretty good at these stuff. They're pretty fast. So we give it time to do this 15,000 times. And what do we get? Oof, it's rough. So yeah, we gave it data between 0 and 0.25. And as you can see, within the range, it's predicting pretty well. But as soon as you go out of it, it's bad. Okay, this is fine though, because most numerical methods work this way. Something worse is we actually need to give it some data ourselves. It's supervised, which is there is some data supervising all of the training process. But usually in physics or in research, we may not have data to work with in the first place. You may just want to probe into what's going to happen, right? So we have to fix this. What can we do? Okay, there are some options. We can increase the training steps. Instead of doing this 15,000 times, we can do it like, I don't know, 50,000, 150,000 times. Okay, I tried that and we still get a pretty bad result. We are still, you know, nothing is helping us in terms of that part. We can give it 50 neurons per 3 layers, per 5 layers. So we increase these layers to 5, right? And we give each one of them 50 neurons, but we still get not so satisfactory results because we're feeding it data. At least we should be getting something more positive in return, because instead of this, we might as well just use finite difference, right? Not in this application, but in different applications, we may just use finite difference. So it's not a good thing. We want this to at least be kind of similar, right? Oh, what about 40 sample points? The same thing happens. We give it more sample points, but we cannot just predict outside. So this is just really obsolete, right? Because it's supervised, which is not optimal. And it's not giving us good predictions outside the thing. So we have to fix either one of them for this to be viable, right? So something else we can do is change the loss function. So the last time I said, we just take all of these outputs over here. We take all of these outputs that the neural network is going to give us, and then we, considering the particular solution of this entire thing, compute the differences, right? The differences squared, and then take the mean of everything. So we may just use something different instead of that, right? So what can we do? So we have a problem at hand, and we have not used this so far, right? We had a very specific equation with very specific initial conditions. Our equation is supposed to look like this. So our neural network is supposed to behave like this as well, right? if you want something good, right? Some good result. We want it to behave like this, at least. And we want the initial point to have the velocity as 0, right? And the initial position to be 1. So we may just use those instead of using the particular solution. So what do? We change the loss function as follows. So whatever our neural network predicts at x equals to 0, we want it to be equal to 1. So if we minimize this, the neural network at 0 is going to converge to 1, right? If you minimize the entire loss function, we have to minimize this. So this is going to get minimized, which means nn 0 theta is equal to 1. That's good. We do the same thing here. The neural network's change with respect to time should be equal to 0, which means velocity. As we minimize this, the neural network is going to give us a physical result, which is why this entire network is called physics informed. And then we want our entire neural network to behave with the given differential equation over here. So if we multiply both sides by the neural network, I know this sounds incredibly vague. How can you multiply it with like an object? But just bear with me. So if you multiply the neural network over here, it's supposed to be equal to 0 as well. So okay, let's just type it in as well. We assume that this is going to get to 0, right? At every single point that we're going to sample. So we take the average of that, and then we just combine stuff together. And then we slap on these lambdas, these hyperparameters, because we don't know how these terms are correlated. Some of these might be way, way, way bigger than the others, and the entire neural network might just want to converge this to 0 and then not work on this, right? Because if you think about it, if this is like around like 1 trillion, then, and this is around like 10, the neural network is going to spend all of its effort into converging this, but not improving this. But we want all of them to be improved. So these hyperparameters are selected usually by hand, which is another thing that we're going to talk about in the future. So yeah, what we're doing here, I should probably tell, is we're choosing specific points in the domain, right? So in this entire domain over here, we're choosing very specific points. And our neural network, if trained effectively, should be behaving like this throughout the entire domain. So that's what we're doing. And we just change the loss function as shown here. We give it the loss function, and then we run the entire program. So what do we see? Now that's some actual improvement. So as you can see, with 5,000 training steps, we're getting somewhat good results. At least in the beginning, we're getting pretty good results. And as we increase the training steps, we're getting pretty good results, as you can see over here. So what have we improved? We don't need anything supervised now. That's pretty good. It still is constrained in a very specific domain. Yes. As you can see over here, when you go outside the domain, it gets really bad. This is the exact solution. This is the neural network solution. It gets really bad outside the domain, but it's not supervised. So that's a good candidate for a numerical method. As you can see, these green dots are the collocation points. These are called the collocation points. The points over here. In all of these points, the entire neural network is supposed to behave like the differential equation. So yeah, that's a reminder. Yeah, and then we have the initial condition over here, the initial condition point. And as we do everything, we get a pretty good approximation within our domain. We still couldn't go out the domain, but yeah, stuff happens. So this shows to be a good approximator within our domain, right? So it's a good candidate. So, okay, damped oscillation is pretty simple. Like every single second year student can probably solve a damped oscillation, right? So we have to try something harder to work that, to show that this actually works. So I actually got this from a paper from Ricey. And Ricey is actually this guy that started everything, these physics-informed neural networks. This is the initial paper that was released in 2018. So what he was considering is, we have this setup, right? We have this single-dimensional, but with changing in time question of like, if you have an initial wave and then you let it to evolve with that is like obeying the viscous Burger's equation, which is a different equation from fluid mechanics. And yeah. Anyways, so we can actually use our PINNs to get a solution for this. So the entire loss function is changed, right? Because these loss functions depend on the problem that we are given. So what he had done is he used the initial condition for the wave, because we are starting the wave with a sinusoidal wave, right? And then we're going to allow this to essentially propagate throughout the space in this viscous fluid, and it's going to evolve. So we start out with this sinusoidal wave, and we want it to behave like a sinusoidal wave at t is equal to 0. So that's the condition here, right? The squared is going to converge into 0 as much as possible by changing these theta. Also, these theta mean the weights and biases. It's the initial condition of the entire neural network. So what is this? This is essentially at x is equal to -1. We want this entire thing to be equal to 0. So these points over here are defined by these points, these crosses. You can actually see them at the boundary, right? And then these points over here at x is equal to 1 are defined over here. And these points over here are defined by these points. So just to visualize everything. And these green dots are these so-called collocation points, which is set up here. And this is actually the Burger's equation multiplied by our neural network. And if this is going to converge into 0, then we can safely say our neural network behaves like the Burger's equation. And when you run the entire algorithm, you actually get insanely good results. As you can see, the neural network obeys the Burger's equation and gives us a really good prediction within t is equal to 0 and t is equal to 0.75. We're actually seeing this shock wave forming, which is a positive thing that shows us this entire thing behaves the way we want it. So that's a good application, right? I mean, it's not a simple problem. It's a problem of like some importance. So yeah, that's good. So what about something more different? Something that is like an actual question. So it's still a fluid mechanics problem, but it's still very hard. It's actually being solved by finite difference simulators. So we are given this initial setup, right? This initial setup space is essentially, we're starting a wave out from this two-dimensional plane, and then we're allowing the wave to propagate as much as possible, right? But throughout this space, we have different regions with different wave velocities. So this wave isn't just going to spread out like a circle, right? It's going to get into all these different shapes and sizes. So we do the entire thing again. We get the boundary data from the finite difference simulation that we're running on like 0.02 seconds, right? Because we need some boundary points. And then we get some collocation points randomly sampled up to 0.2 seconds. And these collocation points have to obey the wave equation, which is defined over here, right? So again, we do a really complex neural network now, because this is a really complex thing to solve. So we give it 10 layers over here, and in total 1024 hidden units, which means 100 and like it can be varied, but like throughout all of these, the hidden neurons should sum up to 1024, which is a really complex neural network. And when we run the entire thing, we get this result. And when we do this on a naive neural network with the the loss function not tailored towards the actual thing, but just, as we have done before with the dampened oscillator, the naive neural network doesn't give us any good predictions, but the physics-informed neural network gives us really good predictions that is kind of on par with our ground truth finite difference simulator. So as you can see, the difference between the PINN and FD is really, really low. I mean, you probably cannot even see it over there, and like the differences here are like so small, it's barely noticeable. And as you can see, it's pretty good, but the normal neural network is really, really bad. So yeah, that's a good application of this as well, of the physics-informed neural networks. So what else can we do with this, the physics-informed neural networks? We may as well just use a finite difference method, right? Instead of doing all of this. Why are we doing all of this? Because training these takes a lot of time. In fact, this was like trained throughout like an hour, which is crazy. FD simulator can do this like way, way, way faster. So why do we even bother with all of this, right? We may as well just use FD. Now, a good thing with PINNs is that it gives you a pseudo solution that you can play around with. It gives you this neural network that is stored somewhere. It just doesn't give you the final condition. It actually gives you something that you can use to probe into the problem, right? So what we can do with this is we can actually reveal some equations, right? We may, starting from that initial problem that we have set, we train a neural network, and then from that neural network, we're going to retrieve the actual equation with everything determined, right? That's important. So what do? We essentially set up a library of operators that we want to solve for. This can be anything. It can be, I don't know, the third derivative of x or second derivative of x followed by the second derivative of y. It can be anything. You set up a operator library that you want to solve for. So this neural network gives you the entire capability of choosing your own solution, even though it may not work as good as expected for some libraries. But anyways, so we set it up like this. We want to solve for this I forgot the name, this operator, this derivative operator, and then we set up the library as this, and then we multiply it by the constants, because all of these single derivation operators are going to have some constants, right? So we set it up like this. So what we do is we essentially run our entire neural network on a different neural network on this loss function. So this loss function becomes a physics loss, right? Because we want this to equal to 0, because we've defined the derivative operator as this, right? This nabla, I think it was called nabla, I forgot. With this times the phi. So yeah, we just set it up like this, and then we run the entire thing, and that gives us a solution for the PDE, which is a good thing. So starting from an unknown PDE, given some initial conditions, a PINN allows you to find some solutions for that PDE, which is pretty cool, right? So yeah, that's literally what happens. So it is obviously too good to be true, right? Like there has to be something wrong with this. And yeah, there is something wrong. It's a numerical method, which is flawed in nature. Every single numerical method, no matter what you use, is always going to give you some kind of approximation. It's not going to be definitive. It's not going to give you the exact result that you would find by solving analytically, right? And another problem is, during this entire process, during this back propagation, where we update all of these weights and biases, we're using something called autodiff, which is a pretty remarkable thing to even exist, but it's really, really, really computationally intensive. And yeah, in higher order derivatives, it's going to take an insane amount of time. In fact, even for the dampened oscillator, the entire training process took me like a minute, which is a lot, actually, considering that we are doing all of this on a computer. So The training time is really high, but the benefits you get from it are pretty good as well because you can solve for equation, right? So another problem is we have to define these hyperparameters. So over here, we have actually, for example, for this solving Burger's equation problem, we have to define all of these hyperparameters, which is not that easy, as said, right? Because there is no set and defined like method to find these hyperparameters. You have to kind of play around with your hyperparameters to see which neural network gives you the best result. So yeah, that's another giant issue with these PINNs. And also, we kind of need enough boundary conditions. Without enough boundary conditions, our PINN wouldn't even work like perfectly because we would only be solving for the equation itself and it's going to be offset, right? That result would be offset. So we need enough boundary points, but we have no idea about how much boundary points is even enough. That's a giant problem, right? So the last one, and this is actually the most important one, is that these PINNs only give us a solution in a very specific problem. So you do everything on a very specific problem, you waste all of this time on a very, 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 very specific problem. That's a problem as well. But there are still some indispensable goods. So it's mesh free. So if some people have worked with some FD simulators before, some of these FD simulators can have like these mesh files of like gigabytes, which is crazy. So it's not that memory constrained, which is pretty good. And it can perform with high accuracy in higher order PDEs. Let me remind you, it's really slow for higher order PDEs, but it's really, really accurate compared to FDs. So if you have like an equation or an initial setup with like really complex high order PDE equation, then you can use this, but you have to be careful that it's going to take a lot of time to actually get some good results. So another thing is neural networks are really, really good at just getting rid of all of the noise and just seeing through the entire data. So this is by nature, since this everything is following the neural networks, it's really good at that as well. So if you have a really noisy data that you want to discover the equation for, PINNs are the best answer. So let's say you're measuring, I don't know, a plasma that is in a tokamak reactor, right? And you want to find out how this plasma behaves. A tokamak reactor is also this plasma fusion reactor that has this insanely hot area. And yeah, it's really chaotic because the entire plasma is really, really hot and it's spinning really fast. So yeah, if you have this tokamak reactor, then you would get all of these noise data. Let's say you're getting all of this noise data through detectors, right? Using those noisy data, you can actually discover some equations, which is pretty cool, and it's a viable application for PINNs. So another good thing is it's mostly unsupervised. So you don't even need some initial data. Sure, having some data is good, but you don't even need them, right? You can always use those collocation points, which are supposed to behave in the way of the differential equation. You can just use them. So, and finally, it's applicable to an insanely wide range of problems. It's actually crazy how many problems you can apply this to. You can apply this to theoretical physics. You can apply this to plasma physics, nuclear physics, thermal physics, and even like fluid dynamics. So it's pretty applicable. So even having a slightest idea of PINNs is a good thing to have a tool in your toolbox. So it can find these pseudo solutions that you can use to interpolate into the data. It's a good interpolator. It can be used to discover equations, and can be used to simplify equations by limiting what you're trying to discover. Because as you might remember, over here, we are setting this library up however we like. We can set this up like in any way we want, right? So this is actually an application that is like kind of considered in theoretical physics currently. If you have this 54-term equation that's like really, really complex and you have no idea what it means, you can train your neural network for you to simplify that complex differential equation into something with like 6 terms. And this has actually been considered in some of the research. And there's this institute called IAIFI that is actually working on this. So yeah, that as a side note. Yeah, it can work to simplify your problems, which is pretty good because some problems have really complex differential equations that you may not even understand, right? Like this, think of this 54-term equation. You may not just be able to write it on the board. How would you even understand it? But if you have the 6-term equation, then it's pretty easy to understand, right? You can try to gain some intuition on that problem. So yeah, and there's this creme de la creme following after PINNs. So it's called operator learning. So what was one of the issues with PINNs? It's only solving for a very specific problem with very specific conditions, right? So these operator learners, although I'm not going to go into too much detail with them, can actually give you a neural network that you can train to find solutions for a general thing. For example, think of the Poisson equation, right? For the Poisson equation, if you give it some initial data, initial differential equation, and then you give it some training differential equation, which you would be retrieving by using PINNs. Using this combination of solutions, you can train an entire neural network on this. So what would this mean is you feed into this PINN a very specific equation that behaves like the Poisson's equation with different initial conditions and stuff. And then it's going to give you the result of that solution, the solution of that differential equation, which is pretty crazy. And this is actually a pretty new field. And like stuff has been like published in like 2021. So it's really, really new. And a lot of developments have been going around in this. So yeah, it's pretty good. This is pretty good as well. So yeah, last remarks. These PINNs are really applicable to basically any field in physics you can imagine. You can probably apply these to biological physics as well with protein foldings because those are going to behave in some differential equations as well. You can apply them to nuclear physics, as I explained before, thermodynamic energy physics, fluid mechanics, and plasma physics. So yeah, they're pretty applicable to anywhere. And the field is really new. It actually first began in 2018, solving very simple stuff. And the last data that I could find was till 2021, but it probably increased by a lot. The number of papers released really increased by time, and the problems that were solved really got more and more complex. So that's a good thing. It's really promising. Another last remark that I would want to make is that I want to emphasize this as much as possible. They're really, really versatile. You can do a lot of different stuff with it. You can find unknown equations, you can simplify equations, you can find interpolations, you can do a lot of different stuff. So yeah, that would be my last remark. Sources and questions.
Does anybody have let's give a round of applause.
Thank you. So don't be afraid to ask any questions because if you didn't have much idea of neural networks, it might have been a little too much. So yeah, you can ask any questions.
I have a question.
Yes.
But does anybody else want to ask a question? Or I do? Okay, here, do you want the mic?
So, what's the status of this model? Are there like mature models that you can basically take out of the box and train, or do you have to sort of build the model yourself?
I see. So, as I've said before, these neural networks, if you are talking about PINNs, they're specific to the problem. And sure, in the literature, you might be able to find some these already trained neural networks that you can just pick up and use. But
no, I mean, not use in the sense that to get result right away. More like the framework itself. Like, what's the state of PIN in general? Like, can I take a template model, train it with my own simulation data,
I see,
and sort of get a result that way?
Okay. So let me actually go back to one of the problems that we had at hand. So over here, not sorry. Over here, we have actually used a really complex neural network, right? We had 10 layers, we had 1024 units. But you wouldn't need this in a different problem. For example, in a damping oscillation, we used a really simple neural network. So the framework, the conditions of this neural network really depends on your question and what you're trying to probe into. So yeah, that's kind of important. There isn't like a cookbook for every single problem at hand. And since the field is really new as well, the literature isn't like too expensive as well. So, and with a lot of these numerical methods, you generally just kind of work with the initial conditions. You tune some hyperparameters and try to find the best solution. Because sure, the training time for this might be a little too long, but when you consider the duration of a research, it's really minuscule. Because 1 hour in your entire paper writing thing is really small. So paper writing time is really small. So yeah, you usually just turn the dials as much as possible to find a good thing. And usually with these, people start to develop a good sense of what to start with. For example, someone that has worked with these PINNs a lot would kind of have an idea of how to tune these hyperparameters, and that just goes for every single data science perspective. This is actually just data science, right? That goes for every single data science tool that you might want to use. So yeah, that was a long answer, but
Right. I have a bit of a skeptical question. I apologize.
yeah.
But so like I've seen machine learning and neural networks and so on used in a lot of different fields.
Yeah, it's kind of boring as well. Yeah.
I'm kind of oftentimes skeptical of it because I mean, I feel like you have some training data and then you feed it into the computer and the computer learns how to emulate the training data. But and that's all well and good for making predictions, but I feel like as a physics person, you should be trying to understand where
the inherent
by
things.
passing the prediction off to the computer. My feeling has been that you kind of are missing out on a lot of the understanding of this, how the system functions, that you would normally get from solving it in a classical way. I mean, obviously you're a more pro ML guy than me. How less skeptical, maybe, let's say. What is your opinion on this sort of thing?
So I would have actually liked to include some additional stuff into this as well, but yeah, I can try to answer that as much as possible. So in theoretical physics, we have all of these different beyond standard model predictions, right? We have these wide variety of predictions, and those predictions, by phenomenology, have some things that we want to at least see. And from the literature reading that I've done, although I'm not fully equipped on like answering this question, but from what I can tell, these PINNs can be used to at least constrain those beyond standard models, beyond standard models to some degrees, because you want to see how they behave as well. So yeah, I don't know if that really answers it, but I'm not too equipped to answer that question. But I've definitely seen some things that actually affects the physics research as well in eliminating some stuff available. Yeah.
That's an interesting viewpoint. I mean, like you can use it to. You have such an incredible power to emulate the data set or whatever.
Yeah.
You can use it to kind of rein in your own
Exactly.
physics.
Exactly.
Well,
Exactly.
That's an interesting idea.
Exactly. Yeah.
More to add to your point, like I don't know if you've heard of the three-body problem.
Mm-hmm.
So that problem, like that comes, there's issue just thinking about it, how three bodies are going to operate for ourselves. So like we're familiar with like two bodies in outer space, but then three body, it's like
It's really hard to even solve. Yeah. Yeah.
So if it gets to like 4, 5, 6, 7,
Yeah.
bodies, like we can't predict that. So I think in that it becomes like really helpful. And even like I've done recent like the asteroid like where so the rate is calculated with models and they include like a lot of factors. So I don't think we can
yeah, with the neural networks, a really good thing about them is that we can really go through a lot of data. We can process a lot of data really quickly, which humans cannot do. Like we are physically limited to do that. So even though it's not like effective in like the purest research, if you're thinking about like theoretical high energy physics, if you're trying to consider some like ADCS, CFT, models, you're trying to make some really high level predictions, then yeah, surely these wouldn't really help you out. But if you consider the broad field of physics research, where you have some like applicable stuff as well, you have some phenomenology, these really come in handy, which is something that they've actually described. Yeah.
I have a quick question about the loss functions. I'm not sure like
This one?
yeah, I'm not sure like my background knowledge. I heard like these like cross entropy loss or like
yeah. So let me show you this. So over here with the dampened oscillator, what we had done is a really basic, a loss function. It's called mean squared error, MSE loss function. And our MSE cross entropy are literally just statistical based loss functions. It's not based on any physical value, so it cannot just try to optimize for this initial condition, right? You would still want to optimize for those initial condition, but when you consider inherently those cross entropy, RMSE, MSE, they do not have these stuff ingrained. So that's what we're trying to do with the physics informed side of neural networks. We're trying to ingrain those stuff into the loss function. So that's why, yeah, those aren't even like considered for these applications. Does that make sense?
loss functions like I'm just a bit confused on what extra terms are for.
Oh, okay. For this, do you want me to explain like them one by one? I can. Yeah, no problem. So for this one over here, as you can see, the NN in parentheses 0, theta. These theta are the initial conditions for the weights and biases, right? This 0 is the x value. So what this means is at the x value, we're taking the -1 and then we're squaring this. So if this value gets closer and closer to 1, you're going to get this value to 0, which is going to help us minimize this, right? So that's what it is. It's the initial position condition. That's literally the same thing over here as well. We're trying to get this to 0 as close as possible. And this one, what we're actually doing is we are multiplying the initial equation over here with the entire neural network. And if you multiply both sides by the neural network, then this side is going to get to 0. So that's what we do here. Multiplying that by the neural network, we want this term to get to 0 as much as possible, right? Which would ensure us that we're obeying the physicality of the initial definition of the entire system as well. And why we have used TIs over here is that these TIs are called the collocation points, and they're sampled randomly or uniformly, however you like, from the entire space that you're trying to solve in. So normally, if you look into a physical system, you wouldn't just see it behaving physically in a certain point and then behaving non-physically in a different point as well, right? You want all of them to be as physical as possible. So that's what ensures over here. And obviously, we take the mean of all of this. So yeah. Does that make sense? Yeah. So you want me to explain the other ones as well? Yeah. So for this one, we're trying to, we're getting all of the points over here, right? These xj's, which are the x points, we're taking all of them, and all of them should behave like our initial condition, which is a minus sine wave. We want it to behave like the minus sine wave as much as possible. So we just subtract them, take their square, take their mean, and then yeah, we get that. So as the neural network gets similar and similar to the initial condition, this term is going to get 0, which is minimizing our loss function. these are all boundary losses as well, by the way. This is the physical loss. So this boundary loss over here is that by our initial definition of the entire system. So we're beginning this entire system by a sinusoidal, like you can imagine this as a 2D thing, a 2D tube, let's say, and then you're letting this sine wave to evolve like in any way possible. So at the boundaries, you're not expecting any values other than 0. At the boundaries, we're expecting the sine wave to be just equal to 0. So that's what we're setting up here. At x is equal to -1 over here, throughout the entire time, which is tk, throughout the entire time, we want all of them to be equal to 0. So that's what we have here. And this is the same thing as well, but just for x equals to 1 throughout the entire time region. So yeah, and this one is the, again, collocation thing. And these, you can see it's underlined with green. These are the green points over here. And you're expecting your neural network to behave like this differential equation throughout the entirety of these green points. So yeah, this is what it is. And that's the entire loss function. If you minimize this, you're minimizing that, which means this goes to 0, which means it behaves the differential equation. This goes to 0, which means it needs to go to 0, which means they're behaving like the boundary. And this one behaves like the initial condition. So yeah. And yeah.
I think you're okay.
Okay, yeah. I'll explain this really, really quickly. Okay, yeah. So with this, we want the this is the initial condition for the financial difference simulator. We get these initial conditions from the FD, and we need some initial conditions, right? So we just do these on like a side machine, let's say, for like 0.2 seconds, or 0.02 seconds. And then we get these initial conditions. We want the neural network to behave like the initial conditions. So this is supposed to all equal to 0. And yeah, that's the thing. And these are collocation points that are sampled up to 0.2 seconds. So you can think of it like being sampled in the XY plane and in the time plane as well. We're, sampling all of them. And then we want them to behave like the wave equation as described here. So yeah, that's the entire loss function. I don't know if that answers satisfactorily, but yeah. No problem.
Last minute question. No one?
On the slide, like you improve the loss function and one graph, how would the verification graph only have goes up and then straight down, or the ones that lost?
So these ones are within the training phase, the training space that we took. So we trained our entire neural network on the x values between 0 and 1, right? And this actually might not be seen from there, but yeah, this is the 1 value, and it goes all the way up to 4. So this is actually outside our domain of training. So that's what is happening here. That I tried to show that the PINNs, just like any other not FD, sorry, any other numerical method, do not work outside the sample space. So this just does not work outside the sample space. I tried to show that as well. So you just cannot use PINNs to extrapolate into some data. You cannot extrapolate into this region. You have to keep it within the training phase that you took. Obviously, you could have trained this entire thing between 0 and 4, and all of this would have made much more sense within this region. Yeah.
Okay. Thank you everybody for coming. Thanks for that. I thought it's an interesting talk. I mean, especially with the Nobel Prize and everything. I mean, with neural networks and physics,
yeah,
it's a big thing.
Yeah.
I don't know much about it personally.
And it's good to be skeptical about all of this as well, because there's this craze in like neural networks that's like.
Well, me specifically,
yeah.
I'm more used to cases where there's not as much observational data.
Mm-hmm.
So the data sets are really hairy. You know what I mean? You can't sort of very close prediction. The training data isn't as good. So.
Yeah, and the good thing with these is you don't need any observations. So that's that's a really good positive
Oh.
thing. Yeah. With DPINs, you don't need any observations apart from the
Oh, I
patient
see what
condition.
you're saying. Well, the other thing is we don't.
Yeah, we don't have the
we don't have the
initial
physics
involved, yeah.
knowledge either.
Yeah, that's true.
Anyway,
That's true.